Hello. I'm going to review summations. For the integration section of the course, we really need to know summations. And so I want to review these. And we're also going to need to know these in the second half of the course. We're going to get up close and personal with summations. And so I want to explain to you how they work. First, let me give you the general idea. What AK is. AK is going to be some formula. So AK is a formula with K. So for example, we have this formula right here. Okay, and that's a 2, sorry. It's hard to read. Yeah, that's a little bit better. Okay, actually let me make this clearer. Sorry to be so messy. So here, AK is equal to 2K plus 1. Okay, so we have some formula. Now N is the stopping point. Here N is 4. K equals 1, that's the starting point. Here N is 1. And so the way you do this is K is your variable, and this tells you to plug in first K is equal to 1, plug it into your formula. Then you plug in K is equal to 2, plug that into your formula, and you keep going. Plug in K3, and you stop whatever this number is. And then you add this up. By the way, this S here is called a sigma. So, and sigma, I'll write that down here. And sigma is an S in Greek. S for sum. So that's where that comes from. So we'll go through here. This is 4 terms. First K is equal to 1. So I get 2 plus 1 plus 1. I'm just circling that's the K. K is equal to 2. So 2 times 2 plus 1. And I keep going. K is next going to be 3. And then finally, K is 4. And I add all these together. 2 plus 1, that's going to be a 3. That's going to be 4 plus 1 is 5. You see the pattern here. 6 plus 1 is 7. 2 times 4 is 8 plus is 9. So I'm adding up odd numbers, 3, 5, 7, and 9. And this is really 2K plus 1 is a formula for odd numbers. So that's not a coincidence. So what I get here is 24. Okay. So one way to do these is just to add them up by hand, use a calculator, which we'll talk about later on in the course, how to do that. And there's some formulas. So what I'm going to do is I'm going to give you a question right here. This was a question that was posed to Gauss. Gauss, who's a famous mathematician, and was posed to him when he was 8. The teacher, I guess, wasn't feeling too well that day and told his students to write down the numbers between 1 and 100 and add them up, figuring it would take him a long time. And Gauss did this in about apparently 10 or 15 seconds and ruining his teacher's day, I'm sure. But so what this means is it means you want to add the numbers 1, K is equal to 1. Then you add 2, K is equal to 2. K is equal to 3. And you keep going and you stop at 100. Now Gauss jumped out and said, 5,050. Now, I was tutoring an 8-year-old once, and I gave him the same question. He said, that's too hard, that's too hard. And then I told him another 8-year-old a long time ago had been given this question. And the student started going, 5,050, and he figured it out in about 10 seconds. So I'm not sure how he did. Well, I know how he did it. But this is one way to look at the problem. This is not how my student did it. So I'm not sure that Gauss did it that way. By the way, Gauss was a famous mathematician, Friedrich Karl Gauss, in the early 1800s, and he was one of the best mathematicians ever. His name is all over the place. So anyway, I'm going to rearrange this and write it a different way. And you'll see where this comes from, and we'll get a formula. So what I'm going to do is I'm going to start writing backwards. I got halfway through, and now I'm starting to write backwards. 98, 99, plus 100. So, well, what do? Well, if I look at this, I get 101. Add this column, I get 101. I get 101. And this keeps going. So I get 50 pairs 101. That's 5,050. Okay. Now, I'm going to use this idea to find this formula. We get n over 2 pairs, 50 was n over 2, of n plus 1. 50 pairs, 101. That's my formula. Some people like to write it this way. Some people like to write it this way. It's either way. So this is the sum of natural numbers. Natural numbers are positive whole numbers, 1 to n. Okay, it's a famous formula. Okay, so you've seen a couple of examples of that. So let me give you another example of a summation. This is a different kind of summation. This is going to be f of x k times delta xk. Now that doesn't mean anything. And we're going to do 3 of these. And these are just made up values. F of x is going to be x cubed, squared, x1 is going to be equal to 2. I'm just making these numbers up. X2 is going to be equal to 5. And x3 is going to be equal to 6. Delta x1 is going to be 1. Delta x2 is going to be 1/2. Delta x3 is going to be 1/4. Again, I'm just making these numbers up. What this is an example of is you might see a summation this way, and this will tell you how to work it out. So, this is going to be equal, k is equal to 1, xk squared times delta xk. Now we don't have a nice formula for xk or delta x, so I have to write it out. So when k is equal to 1, I get x1 and delta x1. When k is equal to 2, I get 5 x2 squared, which is 5, times 1/2. When k is equal to 3, I get x3 squared, which is 6 squared, times 1/4. So again, this is just going to be x1 squared times 1, delta x1. This is going to be x2 squared times delta x2. K is equal to 3, I get x3 squared times delta x3. So again, this is just parenthetically what I'm doing. So I get 5 squared is 25 over 2. 6 squared is 36 over 4. So that's going to be equal 4 plus 12.5 plus 9. That's going to be 25.5. Now again, this is a made-up example. What I'm trying to do is to show you that sometimes our summation formulas are implicit and we have to refer to a function. And then to find out what we plug in, we have to again go back to what those values are. But the principle is the same. First you let k is equal to 1, plug it into the formula. Then you let k is equal to 2, plug it into the formula. K is equal to 3, plug it into the formula, and add it up. Again, that's a little bit of an abstract example. So let me do another example, and here's another famous summation. We won't use this in the course very much, if at all, but that's the sum of the squares. So when k is equal to 1, I get 1 squared. When k is equal to 2, I get 2 squared. When k is equal to 3, I get 3 squared. And I keep going until I get to n, which is my stopping point. Now, I'm not going to prove this formula, but it's equal to n plus 1, 2n plus 1 over 2. Again, so let's do another example. And we will go for, let's say, up to 4 squared. So n will be 4. So we get k is equal to 1, 1 squared. Then k becomes 2. That's how you interpret this notation. And I have 2 squared. Then k is equal to 3. I get 3 squared. Then k is equal to 4, which is also n. And that's when I stop. Now I'll use the formula. I get n, 4, 4 plus 1, which is 5, 2 times 4 plus 1, which is going to be 9, equals 4 times 5 times 9. Oops, sorry, big mistake. That's over 6. Sorry, that formula is over 6. All over 6. And if I multiply this out, I get 20 times 9 over 6, which is 180 over 6, which is just 30. Okay, 16 plus 9, 25, plus 4 more is 29, plus 1 is 30. So quick check. Okay. I'm going to give you one more formula. And this is the sum of the cubes. Oops, I keep doing that. 1 cubed. Sorry, let k is equal to 1. Let k is equal to 2. I get 2 cubed. Let k is equal to 3. I get 3 cubed. And I go all the way up to k is equal to n, which would be n cubed. Now this has an interesting formula. It's n plus 1 over 2 squared. Now, you might remember that you've seen this before. That's the formula we got for the sum of the k's. So this is really interesting. What this is it's just the sum of k is equal to 1 to the n k squared. That's just luck. That never happens again in all these formulas. The formula for k to the 4th is not this squared. It doesn't work for any other one. That's just a coincidence. So it doesn't really help us. That's supposed to be an unhappy face. So the one for k to the 4th is much more complicated. So if you want to do some reviewing of this on your own, do want to do some problems, so some practice, see numbers 1, number 3, number 5 in section 5.2. I'm not going to emphasize computation. What I'm going to emphasize is this kind of thing. And what we're going to see as a preview, so a preview of what's to come next, the next video, is that by definition, the integral ab f of x dx is equal to this bizarre looking object. Now don't worry about that part right there, but that's what I want you to focus on, the summation. That summation is very much like the summation that we have here. Now, this is going to be the next video, and we'll talk much more about that. But that is your goal. Understand is your goal. Okay, thanks. Hope this helped.